Hey Alton, how's it going? Let me just get set up. My other session went a little late. I'm just gonna organize myself. There's the stuff. Hey Samaya, Justin, Diamond Ninja. Tim, how's it going? Labiba, Vicky, hey. Hello, hello, hello. What the heck? Oh, it's tilted. Okay. Nice, okay. Now we're in business. Where are my markers? Oh man, my apartment's getting really messy now. Hey Meg, hey Allie, hey Kim. As usual, let's give it a little bit of time before we start officially. There's like 17 of us. Cool, cool. Let's give it 3 more minutes. Oh no, Rosie. All right. Good morning, Lois. Grandmaster to you, Taz. That's still cooking. Oh, get money. Okay, thank you, Labiba. Okay. Do you want a GM? Then don't work as a public school teacher. Okay. Oh, roasting himself. All right, so today this is Regents Physics. Zero 04 06 20 20. And can you guys read this okay? Just let me know. If you can't, I will switch to a new marker. I'll have to look for it. I definitely have it in here somewhere. But okay. If you can see it, I'm just gonna be good for the environment. And even though it's fading, I'm gonna use it as long as we can see it. Okay. Awesome. I got 1 more minute. Okay, so let's get started. Today it'll be another short lecture because I'm waiting to see if I can get some materials for another demonstration. So let's kind of review so far like what we've done, right? We've talked about, so this will be a little bit of a review and then we'll move on to new cool things, right? So get pumped about that, right? Who's pumped? Tell me in the chat. Here we go, right? So before we even talk about magnets, magnetic force, let's talk about magnetic field, all right? So let's talk about magnetic field. And this is abbreviated in physics with the letter B. What generates magnetic field? We know magnets. And the Earth. And most importantly, we know it's moving charges, right? And the direction of the field generated by a moving charge, thank you so much, guys, for being pumped up. Pump it up. The direction of the field due to the moving charge is given by the right-hand rule number 1, right? Thumbs up. Hey, right? Okay. Now, let's talk about the magnetic force, right? We should know that this is actually, magnets are examples of moving charges, right? If you remember how permanent magnets work, right? It's like a spinning electron, and when the electron spins, it acts like a loop of current, right? And for these two examples, you should be talking about a straight wire and a loop of current, like a solenoid, right? A solenoid is just a bunch of loops stacked on top of each other, right? And like if I have a loop of current, that's the exact same thing as a spinning electron, right? So I'll write spinning electron here. Right, and the spinning electron acts like a loop, which is a moving charge, and permanent magnets have a bunch of electrons spinning in the same direction, so there's a net magnetic moment generated by there, right? Same thing happens inside the Earth, but in a much more complicated way that we can't really model effectively, right? So at the root of it, it's really just moving charges, right? It's like really nothing else. Everything else is like just an example of moving charges, right? So the magnetic force, since the field is generated by moving charges, well, the force, it acts on moving charges. Whoa, Mr. So I thought it acted on magnets. I thought it acted on other magnets, right? I can attract magnets. I thought it worked on certain metals, like iron and nickel and cobalt, right? Well, guess what, guys? Magnets and other metals, the magnetic metals, are just examples of having a lot of charges moving in the same direction, right? So again, the root of everything is moving charges. Magnetic field is generated by moving charge. It also affects moving charge. And what formula describes that? Well, is QV cross V. And this is going to be the right-hand rule number 2. We've learned a lot. I know it's like really cool to see it all condensed onto one page like this, but if this feels like a lot of information, it is. This is exactly what we've been going over for the past like 2 weeks, right? That's a lot. It's a lot of information just to be fitting on one page, right? If that's for a single moving charge, if I'm talking about the charge, this could also equal mv squared over r. If if I have like a field going this way, and I have a charge going this way, and it wants to go in this circle, all right? This also turns into, instead of, if you're not looking at a single charge moving really quickly, if you look at perhaps current moving on a wire, the force on that wire, which is actually consisted of many different, like a huge number of individual charges, this is just becomes the length of the wire times the current times the magnetic field strength, right? So that's the alternate expression of this for a wire, okay? Gold has so I mean, almost anything, any material has like an incomparable number of electrons, right? It has like moles and moles of electrons, which is like 10 to the 23. The only difference between iron, nickel, and cobalt and the other rare earth metals that also happen to be magnetic, like neodymium and stuff, is that compared to a metal like gold or silver or aluminum, or even a more common metal, copper, right, is that for all of those metals, every electron that spins is paired with another electron that spins in the opposite direction, right? These electrons pair up. It's a quantum mechanical property, right? They pair up and they end up canceling each other's magnetic moments. With iron, nickel, and cobalt, what happens is that pairing still occurs, but there's also a bunch of free agents. And those free agents aren't always lined up in the same way. That's why like I can have a random piece of iron and it's not magnetic, but it's possible for them to be lined up all in the same way. And guess what? They don't have like an evil partner that cancels out their field. So in the off chance that they do all line up, then the whole thing can act like a magnet because those free agents don't have partners that are canceling out their stuff. Okay? All right. So that's just a review from everything we've done so far, right? This is how a railgun works. This explains why wires moving in the same direction, do they repel or attract? I don't know. And currents going in the opposite direction, do they attract or repel? I don't know. That's something you're going to have to derive every time. That's not something you memorize. Okay? That's not even something I memorize. So if it's this way, and then this way, sure. Like ones, repel them. I just did that with my right-hand rule. Okay. Today we're going to be going over something completely different, right? And I think I gave a little preview of this last week, but we're going to be going over how electricity is generated. Like, all right, so I know what voltage is, I know how voltage works, I know what current is, I know how current works, but how on earth is my power generated in the first place, right? How do I not, what's the difference between solar power and wind power and hydropower and coal power? Okay, and here we go. All right. So the first thing we have to go over today is this concept, this quantity called flux. There are all types of flux. Today we're going to be going over magnetic flux. Okay. So magnetic flux is abbreviated by, well, all flux is abbreviated by this letter, psi. Okay. Whoa, if you guys can see that. Whoa, whoa, wow. And since it's magnetic flux, it's psi sub b. Okay? And it has a very clear formula. It's just the magnetic field times the area. Right? But if you notice that these are both vectors, And what is the area, right? So this is the area. I would argue that this is the area enclosed by a loop of wire. It's not always the case. Like I can have flux without wire, but that's why area is a vector. We're gonna be going over that in a bit. Okay. So let's pretend I have a magnet here. This is the South Pole. This is the North Pole, and I'm gonna draw my field. Right, there's an example of my magnetic field, okay? And let's say if I have a loop of wire, I'm gonna put this in purple, okay? And I put it here, okay? Or I could put it here. Or I could put it here, or I could put it here, okay? These are all supposed to be the same size, by the way. I kind of screwed up. All right. This is a 3D representation. Like obviously my loop of wire looks like this. And this area equals A, right? And that's going to be pi r squared in this example, but it doesn't always have to be like a circular wire. I'm making it easy for us by making it into a circular wire. No big deal, okay? The area of that vector, the area of this area, the vector, the direction of this area vector is just normal to the surface. So right now, the area vector would point into or out of the page. Here it points to the right or to the left, right? So which one has the most flux? This one does. It has all 5 lines passing through it. This one only has 3 field lines passing through it. This one has 3, this one has 1. Oh, never mind. This one has 1, 3, 5, 7, right? So the more field lines that pass through the area, the more flux it has, right? So flux is a measure, right? So I would argue that flux is a measure of how much field passes through a given area, right? How much. Okay. Why is area a vector? We'll see. All right, so let's pretend I have a magnet here, okay? And that's really hot. I have a wire here, okay? And this wire is broken, whatever. And no, this is no good. You know what's better? This. Let's pretend this is a wire, okay? And if my magnet's like this, there's a lot of flux going on. But if it's like this, if I turn it 45 degrees, right? So it looks like this. The area decreased. Like the area that the flux can go through decreased, but the area of my loop itself didn't, right? Like I can turn this whole setup, and if I turn it a full 90 degrees, like this, then there's no area for the flux to go through, right? It just looks like this, but the area of this didn't change. So the way we kind of talk about that is like, if my magnet's like this and my loop is like this, well, the area vector points this way. And let's go for a bird's eye view, right? This is a bird's eye view. And if my magnet points this way and my loop points this way, the area vector points this way. Right, this is lots of flux. This is some flux. This is no flux at all. Right, if my magnet looks like this and my loop's this way, there's no way for my magnetic field to pass through the area, okay? And guess what? If my B field always points this way, well, the dot product is the perfect way to describe that, isn't it? Right? So remember, like B dot A is largest when they're parallel. And the actual thing is like B dot A is always equal to B times A cosine theta. But the theta here is 0. Theta here is around 45 degrees. So this is the flux here is equal to BA cosine 45. This is equal to BA because cosine 0 equals 1. Okay? And then here, my flux is equal to 0. Right? My flux is equal to 0 because BA cosine 90 equals 0. Right? Please let me know if you have any questions before we move on. This is probably the most complicated thing we're going to be going over. It's a measure of how much field passes through a loop, okay? I can increase how much field goes through my loop by increasing the field, so increasing B, or I can increase A, right? If I make it a bigger area, then it's gonna catch more of the field and give more flux, right? I can also decrease the amount of flux by decreasing the area, but instead of decreasing the area, I can also turn it. So less of the area is effective, right? Diamond Ninja, I have a tea kettle, but I just choose not to use it. Why? I don't know. I don't know. No, nothing broke. I'm just really tired and a lot of it spilled. But I never think it's a problem if things spill, especially tea. It just makes everything smell better. Okay? So as Bob Ross would say, this is just a happy accident. Okay. So let's move on to why these are useful. Okay? And this is going to be like the most important part. So if you have your friends who aren't tuned in, which is a lot because only 26 of you are tuned in right now, tell them 25 minutes is where the important stuff happens. But you probably should watch the first 20 minutes because if you don't know what flux is, then you're not going to understand this next bit, okay? It's called Faraday's law. And it says, anytime I change flux, change in flux induces voltage. So if I have change in flux, I create change in V. This is commonly abbreviated as EMF, electromotive force. It's the exact same as voltage, all right? But some books have it as EMF. All right, Tim, why don't you just go to their channel then and get off this one, all right? You think they're so cool. Just kidding, Tim. Just kidding. I'm really glad you're looking at outside resources. It's fantastic. It shows that you're taking initiative in your learning. Yeah, and I know for any, so if this is my loop of wire and my flux changes, how can it change? Maybe I turned it, maybe I decreased the magnetic field, maybe I increased the magnetic field. It doesn't really matter, right? But if I change it, I've induced a voltage, right? So there is now a voltage here, and because the wire has some resistance, it's super small, but it has some resistance, current will be generated. Yeah. Right, so current's going to be generated in that loop. How cool is that? So I can generate current and I can generate voltage just by changing the flux, all right? And I do believe the formula, let me just double check, right? It's the derivative of time respective derivative of flux equals the EMF times some constant. And I just forgot the constant. Ugh. Oh, it's actually just straight up that. Okay, great. So what this is saying is the change in flux over the change in time, right? So the more quickly you change the flux, the stronger this effect will be as well. This is equal to your EMF or your voltage, all right? This is the same thing, okay? We can't get into that, the EMPs, without going over light waves, right? So we're not going to do that yet. Okay. Now here's the cool thing. Any basic hand crank generator, I have some at school, didn't bring it home, which sucks. Works like this, okay? I basically have a magnet here, a magnetic field. It points this way to this way, it's uniform, so it always points this way. So over here, I have a lot of flux, okay? A lot of flux. If I turn it this way, no flux. And if I turn it this way, lots of flux. No flux, lots of flux. No flux, lots of flux. No flux, lots of flux, right? Do you know what we're doing that whole time? We're changing the flux just by changing how much of the area the field can go through, right? So if flux equals B dot A, there's three ways we can change the flux. We can change B, we can change A, we can change theta. In this ingenious contraption, we are changing theta, right? Woo, 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 woo. We're changing the direction. We're changing how the area vector lines up with the magnetic field vector. And what happens when I do that? What happens when I change the flux? I induce a current. And that current is how I generate electricity. So if you guys remember that video I showed you of the biker powering the toaster, that's exactly what's going on. There is a magnet within that bike, and when he does the bike thing, okay, he's spinning a coil of wire super rapidly inside that magnetic field, changing the magnetic flux, generating the current, all right? Even cooler is, so now you can kind of picture why most electric generators you can think of work in circles, right? So let's talk about wind power, right? Wind power turns these propellers, that turns a turbine. What do you think's in that turbine? A coil of wire in a magnetic field. Hydroelectric power, which is just falling water, okay? What do you think that water does? That water turns a wheel at the bottom, which is attached to a turbine, which is just a coil of wire inside a magnetic field. even the earliest types of solar power, what they were comprised of was mirrors like this, okay? And a pipe of steam, a pipe of water. And when the sun hit this mirror, right? When the sunlight hits the mirror, the geometry is such that all the light focuses on this pipe. What do you think that does? That boils the water in the pipe. And what does that boiled water do? It turns into steam. That steam pushes a turbine. What does that turbine do? Turns a coil of wire in a magnetic field, generates electricity. Even oil, coal, natural gas, what do? You burn the coil, you burn the oil, you burn the natural gas. What does it do? It heats a tub of water that generates steam. That steam turns a turbine. A turbine generates electricity. Nuclear power is the exact same thing. The nuclear reaction generates a bunch of heat, turns a turbine. The heat heats up water, water turns into steam, steam turns a turbine, boom. Almost every form of electricity generation is using Faraday's law and changing the flux to generate a current, right? So when you're talking about the actual mechanics of generating power between wind, solar, natural gas, nuclear, they're all the same, right? We have not come up with a different way to generate electricity in around 100 years, right? It's always been the same way, rotating a loop of current, rotating a loop of wire in a magnetic field to induce a current. The only thing that's changed is how we get that loop of current of wire to rotate and to spin around, right? Whoa. Even when we're talking about fusion energy, nuclear fusion, same thing, right? It's just a way to generate heat, to create steam to turn a turbine. Yeah, how cool is that, huh? Now, there is a second form of solar power called a photovoltaic cell. And that's basically, like, the best way I can describe that is reverse photosynthesis. Oh, no, it's the same. Yeah. So plants convert light energy to chemical energy, right? They like convert that energy into like actual matter and like food that they break down later. And a photovoltaic cell works almost similarly just by converting solar energy to electric energy directly, without the mechanical. So this turns solar energy into heat. That heat turns into kinetic energy, and that kinetic energy then turns into electric energy with the turning of the turbine. The photovoltaic cell, which are like those black solar panels, right? Black and blue solar panels. They skip a lot of steps and they go straight from light to electric. But I think right now it's only like 30% efficient. Like, so 30% of the light energy turns into electricity, whereas our steam powered things they operate around 45 to 50%. So like 50% of this potential energy that turns into kinetic energy ends up turning into electric energy, so forth, right? Yeah, that's basically it. I am going to send you a practice, like a very basic practice about Flux and a power thing, and I'll send that around 2 o'clock this afternoon. All right. If you guys have any more questions, I'd be really happy to answer them right now. And otherwise, be on the lookout. Mr. Ross has been planning a really cool series of videos, and I think we're going to try and like release those either tomorrow or Wednesday, and it'll give you some like light practice and enrichment for the rest of the week while we wrap up magnetism. This is the last week we're going to do magnetism. And then next week, depending on the guidelines the DOE gives us about what class is going to look like, I'd like to start light waves, which I think is one of the coolest units of the year. So get pumped. All right. Who's pumped? Let me see in the chat who's pumped for light. I'm super pumped. Okay, so many cool things we can do with light. You think I actually personally think magnetism is pretty boring. I think it can explain a lot of cool things. I think it is kind of eye-opening to realize that all of our power generation methods are the same. And like it's cool to know how compasses work and stuff, but I'm talking relatively speaking, this is pretty boring compared to light. So if you think this is exciting, prepare to get super excited. Get pumped to get super excited. All right, I can't wait. All right, so yeah, I don't think there should be any questions with this, right? It's kind of simple. Hell yeah, I'm liking all the pumps. All right, I'm counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm counting over 17 pumps and only 5 likes. That kind of hurts my feelings. I also noticed I only have 89 subscribers. Please subscribe. That way, like, I don't have to email you. You can just like know when I'm streaming, and that's pretty cool too. All right. Every power plant relies on steam power. No, Ethan. Every power plant relies on turning a turbine. Most of them do that with steam, but for hydroelectric power, no. The falling water itself, before it even turns to steam, turns a turbine. In wind power, there's no moving water at all. There's no moving steam. It's just the wind, and that turns a turbine. Okay? It's okay. It's a free country. You can dislike whatever you want. Have a great rest of the week. All right. I look forward to seeing you guys tomorrow. Okay. It'll be a regular stream. It won't be like going over answers or something. So just get pumped for that. Right. Have a great day.